Okay, it's 9:01. Hello everybody. Welcome to Friday BEG seminar series. Today is the first seminar. So my name is Won-Hyun Lee. If you have any question about this Friday seminar series, please contact me and or Jennifer. So it's my pleasure to introduce Dr. Quisheng today. He is associate professor in Department of Geography and Sustainability at the University of Tennessee. He is also Amazon visiting academic and Google developer expert for Earth Engine. His research interests include geospatial data, science, open source software development, and also interested in the utilizing big geospatial data and cloud computing to study environmental change and surface water and wetland inundation dynamics. And he has developed and published various open source package for advanced geospatial analysis and data visualization. Please welcome Dr. Wu today.
Yeah, thank you, Dr. Lee, for the invitation and introduction. So let me share my screen. Yeah. Can you see my screen now?
Yes, it
Okay.
works.
Okay, thank you. I also send the link to the slides in the chat, so you can access the slide if you want. Also, you can scan the QR code at the lower right corner. So for this talk, I will cover. Let me see here. I will first introduce the interactive web app that I created. It allows you to create satellite time-lapse animations for any locations around the globe using all kind of free satellite data in the public domain. And then we introduce Google Engine and what kind of things you can do with Google Engine. Then we highlight some of the key features of the GMAP package that I created for doing geospatial data analysis and visualization. And we also show you another package called Segment Geospatial that I recently developed for doing automated image segmentation. And lastly, I will show you some additional resources, even to learn more about some of my open source projects. And at the end, I will have time for questions and answers. So on the right here is kind of a time-lapse animation. So this is the Landsat time-lapse animation annually from 1984 to 2022. And you can see how the environment is changing throughout the year. So this is the river dynamics. This is in Peru, South America. And with cloud computing, you can easily not just visualizing the changes, but you can also extract information. So you can easily, for example, extract the rivers, and you can see how it's changing throughout the year, the size, the shape, the geometry, something like that. If you want to try it out, upper right corner here, there's a link. So this is the link to the interactive web app that allows you to create those time-lapse animations. And I can show you here, this is kind of interface. And there's a demo here. So all you need is to zoom in to any location you like, and then you can just select a region, or you can upload a shape file to a GeoJSON, and then you can just use the area you like, then select the satellite, customize some of the parameters, different band combination, different year, then you should be able to create a time-lapse animation. So look at it like this. So within 20-30 seconds, you can get animation for any location using any satellite available in the Google Engine data catalog. So this might look pretty simple, but under the hood, it processes a lot of geospatial data. So there are tons of data available for specific, for example, for specific year location for the past 4 decades. And it processes the data, remove the cloud, create a mosaic, and then put them all together. Without the cloud computing, so this can take you hours actually to create. So you need to go to, for example, USGS to download the data, you need to figure out where what images covered in the area, and then trying to download all the images, then you're trying to remove cloud. So it's very time consuming. But now with cloud computing, you can do that easily with a couple clicks without having to really download and process the data on your own. And next, I'm going to quickly show you some examples that are quite striking. So on the left side is the drawing of ROC. So most of this set Landsat data, we have data back to 1984 or even 1970s. So we have almost 4 to 5 decades of data that you can see how the environment has been changing throughout the years. And on the right is the mining in Alberta and coastal expansion in Dubai, and also the river dynamic I showed you at the beginning, and deforestation, landslide, urban expansion, the famous Las Vegas urban expansion in China, in Mexico, right? It's very, very fast urban expansion. And besides urban, you can also do some other, for example, coastal change, coastal erosion. And this is especially useful. Everyone can understand, like see it's changing, but I think the more important thing is to answer some of the scientific questions. Why it is changing this way? What are the driving factors? What are the contributing factors to the change like this? So there are a lot of things that they need to be done in order to be actually to understand the environment changing dynamics. And besides this Landsat data, so those are the 30 meter that we have 4 decades, 5 decades of data, but you can use pretty much any satellite data available in the public domain. And as long as Google Sensing has that, or you can upload data to the cloud to do data processing. So this one shows you the NOAA hourly temperature data. So you can also easily see how the temperature is changing throughout the Earth surface within 1 day, like 24 hours. So you can create this kind of animation easily just with a couple lines of code or even no coding. And also, for example, sea surface temperature and vegetation dynamics. So you can see how the vegetation, the phenology changes at the continental scale, right? For example, in Africa, so you can see it's quite dramatic throughout the year. And so those data usually got longer time scale and then the low temporal frequency. But for some of the natural disasters, we might need data that's very frequent, for example, every couple minutes, every hours. Landsat data only provide data images for each location at 2 weeks, roughly 2 weeks. Now we have Landsat 8 and 9, so you have a lower temporal frequency, but still, it won't be able to capture hurricanes and volcano eruption because those things happen very quickly. So we also have a look some other data that specifically for monitoring events like this at a high temporal frequency. So the GOES satellite provide images, for example, every 5 minutes. So this is the famous Tonga volcanic eruption. So you can get images for every couple of minutes, and then you can put them all together, so you can quickly see the impact of the volcano. And also you can do Wi-Fi monitoring. So you can use the same GOES satellite imagery to capture the images, and then you can quickly see how the Wi-Fi is spreading. Besides just capturing the images, you can also do analysis. So here on the imagery, the pink pixels, those are actually the boundary of the Wi-Fi. So you can not just figure out, just looking at that, but you can also do analysis. So there's the two major parts, doing visualization, but also doing geospatial analysis. And again, you can try it out for any way you like, and then you can look at some of the data available in the web app, but there are right now over 90 petabyte data available that you can utilize without having to download or install anything on your computer. So it's just like doing the streaming, but it's streaming the geospatial data. And under the hood, it's using the Google Sensing. So for those of you who have not used this before, it's a cloud computing environment that allows you to process geospatial big data and also do analysis, and you can export the data. You can create a web app, something like that. It's free for resource education and non-profit. You can sign up for an account, and then you can start using it easily. So why do we use Google Sensing? It's kind of similar to the streaming services. So if you're trying to watch a movie, so nowadays you most likely you just go online, Netflix or YouTube or Amazon Prime, you can just search and then you can start watching the movie. You don't need to actually to buy a DVD and to have a computer to be able to actually have the DVD-ROM or Blu-ray or whatever to watch the movie. Now you just a browser, everything can download just within a browser. So it's so much easier, and you can do that anywhere on any platform. So you can on your cell phone, on your tablet, on your laptop or desktop, whatever you like. And so it's been similar in the cloud computing. So nowadays, you can just open a browser and then you can start doing coding, and then you can process a large amount of data without having to have a good computer. So also it's kind of user friendly. So it has a lot of components that allows you to interact with the map without having to trying to do all the coding. So it has the coding, but it also has a lot of components allow you to interact with the data. And so Google's engine right now has over 80 petabyte. I think right now probably more than 90 now. 1 petabyte is the 1,000 terabytes. So it's 80,000 terabyte of data. And if you know how to access the data, then you can basically has all the data in your fingertips. There you can just a couple of lines of code, you can have access to the data, and then you can start doing analysis. It also has API, Python, JavaScript, REST API, and it's also accessible and reproducible. So on the right here shows you kind of journal publications from the last couple years up to like 2022, and you can see the exponential growth of journal publications using Google's engine, either in the title or in the abstract. So certainly a lot of people using it because it just makes it so much easier to do global scale or continental scale studies. And one of the simplest application of using Google's engine is to create, for example, cloud-free mosaic. So think about remote sensing. So cloud is a big problem in optical remote sensing. Anytime during the day, the Earth is covered by a cloud. 60-70% of the Earth is covered by cloud. And if you have a bunch of images, cloudy, even it's cloudy, you can easily create something like this easily. Just a couple lines code, you can get all the images and create a cloud-free images, because it's going to basically do the computation based on each pixel. So each pixel is going to pick the best quality pixels throughout the year, or depends on whatever time span that you specify, and then put all the pixels together. Then you end up with something like this. And this is very common if you're using Google Earth. Google Earth allow you to visualize the data, but you cannot do any analysis. So some of the images you see on Google Earth, some of those actually have been processed using Google's engine just to present you a cloud-free global mosaic, but actually it's not true. So the images, so each pixel might come from a different date. So it's then, although you see one image, but it's like put all the pixels together in order to create something like this. And this is very easy to do. Traditionally, it's going to take you a long time to download all the data to do the processing, but now we can do this just with couple lines of code very easily. And as I mentioned, so Google's engine has a huge data catalog. Right now it has over 80 petabytes. So most of the data set in the public domain are already ingested in the data catalog. So kind of think about like the movie database. Like Netflix is a huge movie database, and you can just search the movie, the name, and then you can just watch it. So same idea in here. It has a huge data catalog. You just search whatever you like, and then you can load the data easily. And then you can do all kind of analysis. So you can visualize that, you can analyze, you can also export the data, or you can also upload the data. You can, if you want to utilize the cloud computing power, you can just upload data and then to utilize the parallel processing. So Google's engine is so very powerful because it's using tens of thousands of servers to process the data. So it depends on the zoom level. So when you zoom into the map, your area becomes smaller, the resolution becomes high resolution, it's going to just compute. So it's essentially subdividing the area into smaller tiles, and then send one small piece to one server, another piece to another server. And then when it's doing the computation, it's really fast, and then just return all the result and then show it on the map. So kind of like you are looking at Google Earth. When you zoom in and zoom out, you see the kind of the images quality changes. So you can go to load different level images. But when you're looking at the global scale, you don't need a high resolution. You just need an overview. But when you look at a specific area, very high resolution, then you're not utilizing the global extent, so it becomes smaller. And at the end, it's just sending those smaller pieces, subdivide into smaller pieces, and doing the computation, get the result back. So that's kind of the under the hood how it actually works and why it's so powerful and faster. One thing I want to here to point out is that so now we already have a lot of set data, but still you can still process those data locally if you want to, but certainly it's going to be very challenging if you're trying to do global scale, for example, doing even using Landsat 8 or 9, because it's going to be hundreds of gigabyte data, and it's still feasible if you do it locally, but in a couple years, it will become even more challenging. So Landsat Next is going to be launched in 2030. And so the resolution is going to increase from 30 meter to 10 meter. So it's like 3 times. And also the spectral band is going to more than double. And so think about the file size increase. So right now, the Landsat 8 and 9, so roughly one Landsat thing is 1 gigabyte. So you're going to resolution 3 times. So it's 3 by 3 going to be 9. 9 multiplied by the double of spectral band. So it's going to be almost like 20 times larger. And so one Landsat thing right now is 1 gigabyte. In 7 years, for the Landsat Next, is going to be 20 gigabyte. And it's going to be very challenging if you're trying to download images like 20 gigabytes just for one small piece. And if you're doing like global scale, it's going to be many, many terabytes. And I don't think desktop computer will be able to catch up. And because storage is easy, but doing the computation, process 20 gigabyte data in your laptop is not going to work. And so this is why it's important to prepare yourself for the next generation of satellite data processing, because you need the cloud to store the data, to analyze data, to process data. You don't want to use local desktop computing to do that because storage and compute is going to be a big issue for you just within a couple of years. And so this just shows you a table, the file size right now. For example, one Landsat 8, 1.61 gigabyte if it is uncompressed. And certainly you'll be over 20 gigabyte in the future. And so that's kind of the brief introduction to Google Sensing and some of the data catalog. So next, I'm going to quickly show you some of the applications, what kind of things people are using Google Sensing for to do some global scale studies. And so I create a GitHub repo that says a compilation of some of the key papers and some of the resources. So you're welcome to check out the link at the top here if you want to learn more about some of those. And so this is one of the key papers of Google Sensing, basically introducing Google Sensing. It was published in 2017, so it's only roughly 5 years. And you can see it's over like 8,100 citations. And so this is just one paper. It's like more citations than most of the people that of the lifetime citations. And it's quite amazing. So that certainly means that a lot of people are interested in that, they're using that. And this is the paper, and also there's another review paper. This one published in 2020 and also review some of the publication, but just within 3 years, there are a whole lot more publications coming up. Just to show you some of the applications, like so we can do, for example, urban mapping, agricultural, vegetation, hydrology, natural disaster, image processing, weather and climate, you name it. So, and pretty much all the geospatial sectors, we somehow you can use Google Sensing. So as long as it's using some satellite imagery, Google Sensing most likely has some role to play because it allows you to easily access the data without having to download them. And also you can do analysis, you can create maps, you can create interactive web apps. So it makes it so much easier to use. Also, here's basically the kind of the pie chart showing you how people are using, what's the applications. So here, for example, vegetation and agriculture, hydrology, land cover. So it's quite popular. Certainly the last couple of years has a lot more, and this might have changed, but just to show you an overview, like what people are using this for to do what kind of analysis. So Google Sensing is best suited for raster data analysis. And this paper here, mapping global forest chains, was published in 2013. So this one was the first paper doing global mapping of forests using Google Sensing. So in 2013, published in Science, and in 10 years, you see it's over 10,000 citations, so over like 1,000 per year. So this is one of the earliest one that utilize Google Sensing. And one nice thing about Google Sensing is it allows you to basically use data to do analysis, and at the end, you can also create some interactive web app that allow people to visualize the data, also do some analysis. So in the past, when we do research, when you publish, right, you have some data, you have some algorithm, you can host it somewhere on your server, but people need to actually contact you, or where can you share the data? Can I download data? And then you need to have software to be able to visualize. But now you don't have to. So you can publish the data directly on the Google Sensing platform, and then just send the link. So anyone with the link can actually go online, and they can zoom in, you can zoom out, they can play with the data. You can also have some functionality allow user to analyze the data. So this makes it really things more reproducible and more accessible. And so user don't have to any his desktop GS or remote sensing software to be able to visualize the data. Again, you are welcome to try out some of those links, and you can also do global service water mapping. This one published in Nature, and again, they also have the web app that allows you to update the data. So provide service water mapping for 4 decades since 1984, and freshwater ecosystem. If you're doing like wetland and other types of research, this might also be helpful. And also doing global land cover. So we have tons of satellite, but satellite is just the raw data. You need to somehow convert the data to some semantic map. So you can do land cover mapping, vegetation, agriculture, you name it. And this is the kind of the new data set that was published by Google Sensing and also the National Geographic, is to classify every Sentinel-2 imagery. So 10-meter resolution, so it's kind of near real time. So once you get the imagery, they classify, and then can easily use to do some analysis how the land cover has been changing. And we don't have time to go into detail. So basically, you can classify the imagery into different classes, and then it's unlike an annual land cover. It's like real time. So you get an image, you classify, and you get the result, and then can do analysis. So this also shows you some of the output. I can visualize that. You can compare different time periods, and so depends on how many images you have, you want to have how many land cover maps. So this is also one of the very recent applications of using Google Sensing, and you can also mapping wildfire, volcano, something like that. So you can monitor, and then you can also allow users to see the data. And some of those are actually integrated in Google Maps. So if you have any wildfire, and then sometimes happening, people search the places on Google Maps, they will also show you some of these results that have been processed by Google Sensing. And also air pollution, for example, quite interesting, studying the air pollution during the pandemic. So you can see how the decrease of air pollution when everything is locked down. And also weather inundation dynamics. So this is one that I published a couple of years ago using Google Sensing to map high resolution surface water dynamics and also wetlands. If you're interested in, you can look at that. So basically, you have multi-temporal high resolution area images, so you can see how the wetlands or the surface water body have been changing throughout the years. But during the dry year, they might be disconnected. During the wet year here, on the lower left corner here, you can see they're all connected together into a large water body. And so you can actually use Google Sensing to automatically map this one. You can figure out how many times each pixel or each location was flooded throughout the year, how many times. So it's more like permanent water, temporary water, or seasonal water. So those are things that you will be very challenging to do in the past if you're trying to process a large area. But now you can do it, pretty much everything can be automated. But again, it's not perfect. You still have to do some maybe fine tuning, but this save a lot of time that you don't have to download tons of data. You just use it, and you can analyze, you can get some result, and you can go back, you can fine tune your algorithm. And this shows you some of the sample results, right? So you can give it an imagery, you can detect a surface water body, you can get the area, you can get the size, you can get the shape. And on the right here shows you some of the so-called water occurrence. So how many times that each pixel was flooded, right? So the blue color represents it was detected all the times over all the images. So that means it's like permanent water, and others like along the borders, those are usually temporal or seasonal waters because it's the area is very dynamic, so it's changing throughout the years. And so those are some of the applications. Of course, there are tons of other applications. Like I said, there are thousands of journal publications every year using Google Sending. And so next, I'm going to introduce GMap. So this is a package that I created a couple of years ago that utilizes Google Sending but can do a lot of visualization. So so Google Sending had a JavaScript API and also the Python API. When I got started in, I think, 2018, when I first learned Google Sending, most of the documentation at that time was JavaScript only. So, and for Python, they are very limited documentation. So JavaScript, they have a lot of documentation, they have sample codes, and it's very easy to get started. But personally, I prefer Python, and because it's easier to learn, and you can do batch processing. You also has a lot of library you can choose from. You can also integrate desktop.js, QGS, ArcGIS. Also, you can do deep learning. So, and also you have a lot of IDE to choose from. JavaScript, you are limited to the web interface, but you cannot really communicate with your computer. And so at the time, Python has limited support. So I spent some time learning some of the packages and trying to develop packages that have some equivalent functionality. So mostly focusing on visualization, but there are also some data analysis functionality. So if you see here, this is the interface, the main interface of the JavaScript API. So JavaScript API, you can think about it has two components, doing visualization and also doing analysis. So analysis, basically you're writing sample codes or source codes in the interface, and you can see the map, you can visualize the data. But the Python API doesn't have that functionality. So you can basically just do computation. But if you want to visualize the data, it's kind of challenging because it doesn't provide you the functionality to do that. So I built on top of some of the mapping libraries and then connect it with Google Sending, and then so makes it really interactive and easy to use, so that you can basically have similar functionality compared to the JavaScript API. And so the project is hosted on GitHub, so you're welcome to check out the GitHub repository for more information. So you support anywhere they support Jupyter Notebook or Python or Google Colab or whatever cloud computing environment you're using. And there's also a website, gmap.org. Has a lot of documentation, tutorial, examples, API references. So I recommend if you want to learn more, you can check out the website. And I also published a short paper describing what GMap is and what kind of things it can do. I was lucky to have some funding from NASA to support the development and maintenance of the package for 2 years. And so during the past couple of years, I've developed a lot of tutorial for Google Sending and some other open source. So you're welcome to check out my YouTube channel for more information. Has over 500 videos, so you can pick whatever you might be interested in. And so specifically for GMap, there are over 130 tutorials. So each tutorial has a Jupyter Notebook that you can reproduce what I did in the notebook, and also a video, usually 15-20 minutes, that if you want to see how to do that step by step, you can try it out. And also give animation showing the highlights of the tutorial. And I also published a book last month introducing GMap and Google Sending. So if you're interested in it, you can check out the link upper right corner here, book.gmap.org, so you can get access to all the source code. If you want a hard copy or PDF, you can also purchase from the link in here. So this is, it took me a couple months to put all the things together, but it's give you a comprehensive introduction to Google Sending and GMap and Python. So how you can utilize the cloud computing to do some large scale geospatial analysis. And by the way, so I want to point out that GMap has been authoritative by Google Sending. So it will appear on the documentation in a month or two. So and I'm working with Google to actually restructure the package, and so to extract some of the core functionality. And so going forward, Google Sage is going to use GMap for all their Python documentation. So they have JavaScript, they have Python. So in the future, Python will be just using GMap. So if you really want to learn it, GMap might be very useful for the Python if you're doing Python programming. Next, I'm going to quickly show you some key features. So just to give you a visual impression, what kind of things the GMap can do. So the first one is to automatically convert JavaScript to Python. If you're already using Google Engine, you're using JavaScript, you're interested in using Python, and this might be helpful. So all you need is just copy any sample code from the documentation and then just paste, just convert it to Python, and then you just run it, you will see the result. So in that way, you don't have to learn both. They're pretty much similar, but still, it's going to save you some time without having to manually do the conversion. And you can also do source data set. So this is kind of like similar. You are searching a movie on Netflix, but you're searching geospatial data from the Earth Engine data catalog. And then you just select, and then you just import, and then you just click a button, then you can visualize the data. So it's not just for visualization. You have the access to the data, so you can do all kind of analysis. You can do all the statistics, or you can do any geospatial data analysis that you want that's supported by Google Engine, or you can also build your own algorithms, and then you can visualize the data layer. You can change it interactively, and you can turn the data on and off. You can also inspect the data. So this is like, if you really know how to extract data, now you don't need to download, right? So think about this simple lane cover. It's many gigabytes, but you can just one click, couple clicks, and now the data can be displayed on your computer. And you can customize it. You can different color, different visualization. So there are a lot of things you can do to customize the what it looks on the map. You can also use the inspector. So if you're doing remote sensing, sometimes you might want to inspect the pixel value, see the spectral signature or something like that. So this allows you to easily load the data, and you can quickly inspect the data. So it's different from like traditional desktop computing, because the data already hosted on computer. So it's very easy, just click and then get the pixels. But in the cloud, all the data in the cloud. So what is doing under the hood is to, when you click your mouse, get your coordinates, and then send the coordinates to Google Engine, and then do the computation, get the result back, and then display on your computer. So certainly you need to have internet connection to be able to do that. You can also plot data interactively. So if you have you want to check the spectral signature. So if you click, you can do a multispectral. For example, this is for Landsat data, but you can also do it for high-speed spectral. So this is useful if you want to inspect some of the spectral signatures of different features of different data set. And this, you don't have to do coding. So again, it's just getting all the statistics, getting the result, and then return it back to your the map. And you can visualize raster data, vector data. So you can load any, for example, here, DM, and then you can just use the interface to change the color. So it's kind of similar to using desktop GS. You have the data, you want to change the color map, you want to classify into different classes. So GMap also allows you to do that pretty easily. So you can do that for a single band raster, or you can also do it for a multispectral band, right? So if you want to change the band combination, this shows you easily. So you don't have to do coding. So the idea is that GMap makes it easy for you to, you still need to write a couple lines code, but it simplifies a lot of process. So it's basically user-friendly for beginners. If you don't know a lot of coding, you can still use the interface to manipulate the data, to visualize the data, and then to do some simple analysis without having to download data. And besides raster, you can also do, for example, create some map to compare the data. So you want to compare the lane cover changes or natural disasters before and after. So you can quickly, this is basically just a couple lines code, then you can create something like this, very effective. So you can showcase the changes, you can display different data layers, you can compare them side by side. You can also have color maps, color bar, or you have a legend, for example, here low right, just to show you what it is. And it also, you can integrate it with desktop JS. If you already use ArcGIS or QGIS, so also has plugin that allows you to actually use desktop JS to retrieve the data from the cloud, and then you can load the data layer. So in that way, you can overlay multiple data layers together. So you can have data from the cloud, you can have data on a local computer, and then you can use that to do create some maps. And so in that way, you don't have to download data because some of those data might be many gigabytes, and it's just it's going to take you a while to download the data. But now you can create maps using a combination of cloud data and also local data, just like the same way that you do access the data locally. And you can also use Google Sensing GMap to create, for example, some high quality publication maps. So if you need some data for specific projection, need specific data set, you can customize it. You can do whatever you need. And this can be useful if you are using it for journal publications, for project report, whatever, then you can customize to create like this pretty easily. And again, so all the demo that I show you, upper right corner here, you should be able to have access to the Jupyter notebook, the video, and the GIF animation. So you can reproduce everything I'm showing here easily just by running through the notebook. And this is probably the last one. So you can create your web app and then you can deploy on the cloud and then send the link to anyone. So they don't have to be able to do the coding. So you can just do the coding and then create that and then share with anyone. They don't have to have a Google Sensing account, but they just need a browser and then they can visualize data they created. So this is useful if you're doing writing journal publications, you want to share data with some other people anywhere around the globe and you create some apps. So this is super easy. It's just you can check out the repo and some of the examples I provided, and then just easily create an app, deploy it in the cloud, and it's free. You don't have to pay anything, but you make your research products much more accessible to the wider audience because they just need a URL to and a browser to see the result without having to have a good computer or have the account to access. So this is about the GMap, and so there's, if you want to learn more, get your hands on. I gave a workshop actually in July in Austin, so UT Austin, the Sci-Fi conference in July. And there's a the notebook in here that you want to try it out. And also I recorded the workshop. It's 4 hours, so you can go through that if you have time to basically learn all the key features of GMap and Google Sensing. So how to access the data, how to analyze, how to export the data, something like that. And that's about GMap. And next, I'm quickly show you another one called Segment Geospatial. So this is a new package they created, I think, a couple months ago, doing image segmentation. So the idea is that we want to use some so-called foundation model. So Facebook AI, Meta AI released the segment anything model in April 2023 and was trained on 11 images, 1.1 billion segmentation mask. So if you want to try it out, you can check out the link here, segmentanything.com. What it does is basically give you an image, I segment it into objects. And you don't need any training, you don't need any additional training data or testing data. You just use the foundation, so-called foundation model, and then you can do segmentation. It's not designed for geospatial data, but it performs pretty decent for geospatial data. And I built the package on top of this one, and then allows you to basically segment any geospatial data. And you can also get the label. So here, this the GitHub repo. You're welcome to take a look at the source code. It's open source, so you can also welcome your contribution. And so next, I'm quickly show you some of the demos. So for example, giving every image, you can segment it into mass. So basically different objects, and you but right now it doesn't know the label, so it doesn't know it's the building or it's a tree or whatever. But it's a segment into a bunch of objects. So this is more like the traditional image segmentation. But the nice thing is this is geospatial data. So every result, the result that you segmented, it's also geo-reference. And also you don't need additional training. So just a couple lines code, you can segment it, and then you can assign the label if you want. So this is so-called automatic mass generator. And you can segment, for example, buildings. It's certainly much better than pixel-based. This is kind of an object-based segmentation. So buildings, and maybe agricultural field boundaries, right? So you can segment those things nicely, and then you can extract more information from those objects. And this is basically segment everything, but you can also do that selectively. So here in this imagery, you just want to segment, for example, the buildings. You can place a couple markers on the map, And then basically this is the foreground, the object you want. And if there's any extra things you don't like, you just click the background marker and then to remove that. So you can see I can easily extract the buildings. And you might notice I don't select all the buildings. And you just need a couple of those, and then you will segment all the buildings within the map. So in that way, you don't have to have the sample point for all the buildings. Of course you can, but it's not necessary. So this is called the interactive segmentation. They can segment buildings, trees, whatever you like. And you can also do text prompt segmentation. So given set imagery, you can just type, okay, buildings, then it's going to segment buildings. Of course, it's not perfect because it's foundation model. You need to do some fine tuning, but you can adjust the parameters. And for example, trees, just enter trees and then you segment the trees. Adjust the parameters, usually get better. So there's no one size fits all, but you will need to, depends on the imagery, depends on the area, you might need to fine tune that. But think about that. In the past, if you're just trying to segment trees, you need to build more, you need to have the imagery, you need to build a deep learning model or pixel-based or whatever. It's going to take you a while because we don't have a lot of training data if you're starting from scratch. And this is just using the foundation model. So just combination with other deep learning, then you can just easily just type the label, the text, and then you will give you the result. So under the hood, you use a lot of AI and latest computer vision techniques. And so for example, swimming pool, right? I want to extract swimming pools or solar panel or buildings or trees, just a label. And then you can get the result. You can also do some post-processing. So for example, I get a swimming pool. I want to regularize the boundary. You can also do it easy, and then you can export the result. So in that way, you don't have to do manual segmentation, and you can do this at a large scale. So you can at a city level or at the county level, something like that, easy to detect some of the features that you are interested in. Also, you can do batch segmentation. So this requires GPU resources. Again, there are also notebook in here. If you want to try it out, you can just go online. You can do it interactively using Google Colab. And so if you're doing a large area, you can subdivide into smaller sections, and then you just segment each one and then put the result back. So in that way, it's you can do that with a smaller GPU, but you can process a large area. And this is basically using the text prompt segmentation. So you can segment all the trees on the imagery for a specific city, a specific area, just a couple lines code and then get it. So without having to train the data, build your own model, and then you just use the original model. And that's what I want to show you. Again, you are welcome to check out the report for more information. I already provide some of those Jupyter notebook that allows you to easily run that in the cloud, and you can test it. You can do it for anywhere. So you can download any base map imagery and you can test it, see how it works. Lastly, I want to show you some additional resources. So here I created a GitHub organization that hosted some of the packages that I created. So mostly Python packages, but also some data catalog, some web apps and ArcGIS toolbox or R packages. So you're welcome to check out the link, and welcome your contribution if you see anything that you can help with. So the idea is to make it easier for people to access data. So because we have a lot of data in the cloud, so how to actually figure out where are they, and then how to access data in those programming environment, and how to make it easier for people to visualize the data, analyze the data, and also create a web app so that you can present your output, your products to other people, show it to other people, and just using a URL. So they don't have to know how to do programming. They don't need to know the desktop JS or cloud. You just make it easier for people to access that. Okay, so that's what I want to share with you. If any questions, happy to answer your questions.
Thank you for your talk. So we open the Q&A session. So one question at the chat from Alexan. What's the minimum image resolution or zoom level for SAM to get reasonable result? Do you need to also rectification first?
Good question. So it depends. So if you, for example, if you want to get very detailed building or something like that, definitely need high resolution area imagery or drone imagery, something like to do that. But you can also segment satellite data, for example, Landsat, Sentinel. So it depends on resolution, and you will be able to segment the object based on that. You don't necessarily have to also rectify them first. It depends on the image. It's already also rectified. It's great. If not, they may some like shadow and other stuff. It might affect the result, but you can always fine tune the parameters. So earlier when I saw the demo, like the tree, you can actually adjust it and depends on parameters. So you might be able to find some optimal parameters that works best for the case, either it's trees or buildings or water body or something like that. So it performed pretty well in a variety of applications from satellite data, coarse resolution, 30 meter to 10 meter to 1 meter to sub meter resolution, or even just regular photos, even though they are not trained on geospatial data, but it does pretty well. But it's not perfect. So certainly, if your task is very specific, sometimes the dedicated deep learning model might be better than the generalized foundational model because it's not trained on the data, some of those objects that you want to detect.
Okay, any other question? So one more question in chat. Does the Gmap interface have functionality with non-public remote data sets such as Planet or Maxar?
So, yes. So for example, if the data is not public, you can upload data to your account. So for example, you upload your Planet imagery or Maxar imagery into account, but you can so Google Sensing Gmap can also access the so some of the Planet imagery for the tropical area is free. So you can actually it's already in the Google Sensing data catalog, so you can directly access that. So for Maxar data, there are some data in the public domain. You can also, because they are cloud optimized GeoTIFF, you can actually use it. So we can come back to show you here. If you look at the GitHub, the repository, and you will see at the bottom here, Maxar open data. So Maxar open data provide those data for some of the natural disasters, and it's free, it's open access. So you can actually just display, you can grab the data, you can display on Gmap. I also have another package called LeafMap, also can do the visualization, but it's not for Google Sensing. You can do that for AWS or Microsoft Planetary Computer. So you can do other platform. But the answer is yes. So if the data, you want to use cloud computing, then you need to upload data to the Google Sensing data catalog. But if it is already cloud optimized GeoTIFF, then you can directly pull the data in, you can visualize without having to download data. So in that way, it doesn't have to worry about where the data it is, as long as it's cloud optimized GeoTIFF. So Gmap can visualize and display on the map in combination with the other data layers.
Okay, Katie, you have a question?
Yeah, just like everyone else, I mean, mostly comments, which is just that this is great work. This is awesome. And I look forward to looking through the slides more. Yeah, this is really great.
Thank you.
Okay. I think the one more question in chat, is there some kind of safety plan in place so that we don't have to worry about Google deciding one day that this is not an important product for them anymore?
Yeah, good question. Certainly a lot of people have concern about that. But Google have, at least from what I know, is that they're not going away anytime soon. So they still want to commit it to provide free for research, education, and non-profit. So now they actually have the commercial offering. So I think it's a good thing because there's no free lunch in the world forever. And so it has been free for since it launched in, I think, public 2014, something like that. So it has been almost like 10 years. It's still free. But there's no guarantee, right? Sometimes they can stop working, but they said it will still be free for research and education and non-profit. And they have a commercial, actually, it's good because it can offset some of the costs to maintain and develop this, and they are also putting a lot of resources trying to improve and the documentation data set. So it's actually growing. And to me, I think I don't really have a big concern. If it really happens one day, Google Engine go away, there will be alternative. So now we can also do AWS. You can also use Microsoft printed computer, but those platforms are not as popular as Google Engine because it's relatively not as easy to use as Google Engine. But some of the concepts, some of the ideas are kind of similar. So I'm pretty sure if there will always be some alternative coming up in the future, and it might be made even easier. But right now, Google Engine is the dominant, and I'm not really concerned that it's going. It will not. I don't think we stop offering, but certainly you can still provide free, but you can limit the quota or the resources that you can perform. When it first got started, it was really fast and not many people are using it, but now there are tons of people using it. So certainly the allocation they get to each individual, it becomes smaller and smaller. But still, you can actually access the data. If you're not doing very intensive stuff, then it's going to be very, very fast, right? Just think about, you can basically watch any movie on Netflix for free, and you can stream any geospatial data, you can visualize that. But if you're doing computation, then you need to actually learn how to actually do computation. But in terms of visualization, you don't have to download any data. I can see any data with a couple lines code and any satellite data set, right? In the past, you have to download, go to USGS, you can only get a thumbnail of what it looks like. But now you have access to original data. I think just one aspect is super useful, and coupled with some analysis you can do. It's like, why not? But if it goes away, I will find alternative. I'm not really worried, but at least from the near, like in the foreseeable future, I don't think it will go away. So, and also in several couple of years, right? Lansat next, you're not going to be able to do it locally. So certainly, if not Google sending, there'll be some of the cloud. So if you really want to adapt, then you need to have some kind of cloud processing functionality or capability to handle those large amount of data into the future.
Okay. So one more question from Ben. Do they plan to increase user alert quota limit?
That depends. So you can certainly reach out to them to increase the quota. But usually for me, I will just look at your algorithm, how to optimize your algorithm, because sometimes for new users, they want to introduce one because they're writing codes that are not optimized for cloud. So if you know Python, you will do the looping, you do the for loop, those things doesn't work. It works on Google Engine, but it's not efficient. So you need to make sure that use some of the best practices, learn the best practices of Google Engine. So how to do parabolic processing rather than doing like looping and then wait until, because it's not efficient. And those are most likely to run into memory issues. But if you really, your algorithm is already optimized, you're doing global scale, it doesn't work, then yeah, just doing smaller one, doing in smaller pieces. So in GMap and also in the book, I also, for example, how you can do, like, for example, you're doing global studies and then mapping something, it's just too much, doesn't work. It's subdivided into smaller sections, and then you can do it one by one, and then eventually you can export the data, you can put it back together as a GOT. So there are some workarounds, and certainly it's understandable, because think about, you're trying to do global scale, you're trying to load like 10 terabyte data, and then trying to do analysis all at the same time, because it's a free resource, and there's so many people using it. You cannot just take all the resources. Just like there's a free movie theater, right? It's like people are sharing. You only need to watch the movie, but you cannot just say, "Oh, this is my theater. I want to use it." That it doesn't work. You can certainly use some of the commercial stuff, but for me, most of the time, I think the open free one is enough. You just need to know how to make your algorithm really efficient, utilize that. And if it doesn't work, have some workaround. Again, it's not perfect, so Google Sensing cannot do everything that we want to do in the traditional remote sensing, but it takes a whole lot of time away that you don't have to manage the data. So in the past, we have to spend maybe 70, 80% of the time just to how to download data, how to do the processing, how to store the data, and then maybe only 10, 20% really thinking about how to address some scientific questions. But now, like, I don't have to worry about data. It's just like, I can start just load the data, I can do analysis right from the beginning.
Okay. Just reminding that Dr. Wu provide today talks material, so you can check it out the QR code, Katie. So I think
There's one last question from Yang Kan Chen about some of the limitations. Yeah, I didn't mention that a whole lot. So, but I can say that Google's engine is this kind of cloud computing is best for doing image processing, doing location-based or time series. So think about when you're doing the cloud computing, under the hood is basically just subdivide images into smaller pieces and then send it to like 1,000 server and then return the result. So if you're doing something it's best suited for something only related to the location itself, doesn't relate it to its neighborhood or it's something far away. Because if you're related to something far away, they cannot really subdivide. You need to put all the data together. So Google's engine, for example, is not good for hydrological analysis. If you're trying to delineate surface like depressions or flow paths, so you're trying to figure out where this water is going to like flow to somewhere, the outlet to the ocean, then it's going to be very far away. So it's hard to subdivide, then it's not good. But if you're simply just doing like time series analysis, I'm going to figure out how for example, the vegetation changes in this location, then it's easy to subdivide. It doesn't have to worry about the neighborhood. It's really suitable and fast. Also, it's not very good for vector data processing because vector is, unlike the raster, you can easily subdivide. Vector is a little bit more challenging. So, but nowadays it also has some functionality for doing some vector data processing. But to me, mostly focusing on raster data and utilize what it does best. And for some things that is not suitable, then you maybe export the data and then do some other like open source packages. But still, if you're doing large area, you need to load all the data, you need to fit into the memory. So if, at the end, you still have to think about how to optimize and how to have some workarounds that you can do large data processing that's not suitable for Google's engine. So just keep that in mind. Like it cannot deal with neighborhood. It's smaller neighborhood is fine, but if you're dealing with like 1,000 meters far away, it's not going to be suitable because you will need a lot of memory to be able to load all the data all at once into the server to be able to do the data processing.
Okay. Thank you very much. Today's talk, very informative for us.
Thank you.
Yeah.
If you have any questions, feel free to reach out to me or you can connect with me on social media or LinkedIn or just email me. I'm happy to share with you.
Okay. Thank you very much, Dr. Wu.
Thank you, everyone. Take care.
Yeah. Bye-bye.